Today I want to talk about relays, especially on cars, but in some ways just in general. I had a question from someone on my channel asking about relays and if I could give some explanation. So I thought, yeah, it's a good time. I have a small relay here in my hand that came out of my late model Suburban. We'll discuss that one in a minute. Here on the 3rd gen Camaro, we don't have as many relays as they have in a new car. But I got one in the back here for the fuel pump. I have one over here on the right hand side as part of the air conditioning system. There's one down on my car down here behind the headlights and next to the radiator. That is the fan relay. Controls the electric fan you see mounted there. And inside, in the under the dash with the fuse panel and so forth, there's a horn relay, and there are probably some others that I hadn't thought about yet. There's one for the hatch, for the electric release on the hatch. So relays are an important part of our cars, and even outside of cars, an important part of electrical equipment in general. You have them in your, usually speaking, you'll have them in your thermostats, you'll have them in your furnace, you'll have them in your air conditioning of your house. So it's a pretty important device, and we're going to dig in here a little bit and see if we can understand them better. So relays, what are they? How do they work? Why do we use them? Why are they even there? Right? I got half a dozen of them in my car, and I'll tell you, my Suburban, they're probably several dozen if you go through and count them all up. The more modern the car, the more relays that you have. So what is a relay? I mean, in basic terms, a relay is a device that controls a higher current or a higher voltage device with a lower power signaling circuit, we'll call it. And so, gee, what does that mean? There are a lot of places where you have a device that draws a lot of current. If you're outside the automotive world, or if you're in my hybrid and electric world, where I used to be, where you've got high voltage batteries, for example, relays are an essential thing. The simplest example is your starter solenoid and relay. Now, some cars, like my old Ford, had a starter relay up on the fender and a starter solenoid down on the starter motor, and that solenoid would engage the gear into the flywheel and turn the motor on. But it was triggered by a relay that was up on the fender well that had just, a low current, and that would take and trigger the battery voltage and send battery voltage down to the starter motor. On most of the GM cars, the solenoid is actually a relay and a solenoid in a single package. If you go back to cars of this generation, some of the modern ones, they've changed that. But in most cases, the solenoid is a big coil of wire that is an electromagnet that sucks in a core and makes things move. But the old Delco starter motors, the relay and the solenoid were all together in one package. So why do you do that? Well, starter motors draw 200, 300, 400, 500, 600 amps. Shucks, back when I was working on gas turbines, we used a medium-duty truck motor, was the starter for a gas turbine. That thing drew 1,500 to 2,000 amps. Now, at a car level, depends on how cold it is and how loaded it is, you got a few hundred amps. Do you think you really want 200 amps and the number 4 size cable for the battery running through your car, up the steering column to the ignition switch, and having an ignition switch about so big? It's not practical, right? So the relay allows you to run a low control voltage up to the ignition switch, or a low current, still 12 volts, a low current to the ignition switch that will go back and signal a device that turns on the starter motor and lets the high current run down to the starter motor. We didn't need a lot of relays in a lot of these older cars. I'll say before before fuel injection, before ECMs, we didn't have many. Oftentimes you had a horn relay. Sometimes cars would have a headlight relay, but there weren't a lot of them. As you move into ECM controlled vehicles like this, as we got into the 80s and beyond, again, the fan on this car probably draws 15, 20, 30 amps. I haven't actually checked it, but typically they'll run 20 or 30 or 40, even 40 amps, depending on the size of the fans. And again, the cost and the practicality of putting a transistor switch in the ECM to switch 40 amps and send it out to the fan is prohibitive. It just doesn't make any sense. So you've got a small ECM, it can send signals out at 12 volts or at 5 volts or sometimes even lower, but typically it sends out 12 volt signals at low current. And so you can have a modest sized transistor circuit with a driver that will send voltage in the ECM. The microprocessor sends out a signal on its circuit board to a transistor circuit and tells the transistor to turn on. When the transistor turns on, it sends 12 volts out to the fan relay that energizes the coil and makes it operate. Or, be careful with ECMs. ECMs, there are two ways. One is they send out a power signal. The other is the transistor makes a connection to ground from something that's got 12 volt power on it, and they bring it to ground to complete the circuit. You can either feed power or you can sink power. So there are many things where you want the ECM to be able to use a small power to command a big load. And that's one of the reasons on the modern vehicles, the more modern than my 1985, right? That's the reason we have even more relays, because today, well, go back to my Suburban 2019, you have a body control module and a transmission control module and an engine control module. You have a whole bunch of them. But the body module controls all of the lighting. It controls all the body functions. And again, instead of using big switches, you signal the body controller with a small switch. It sends out a signal to one of these relays in one of the electrical centers. And then that relay clicks in and sends power to whatever you want. Hybrid and electric vehicles, this one's a little bit of a different animal. They call them contactors, and a contactor is really what you would call, it's a special purpose relay, and it's got some other safety related components and so forth, but basically it's a big honking relay, and you use it to isolate voltage. The hybrid systems I was working on, we had 42 volt systems, 86 volt systems, 120 volt systems. The battery electrics go 200, 400, 600, 800 volts. When you want to turn the battery on and off, or connect it to the system or disconnect it from the system, you want to send it a 12 volt signal and pull in a 100 volt battery. And you don't want that 100 volts, you don't want to run 100 volts up to a switch on your dash to control whether the battery comes on or not, right? So again, you have a controller, solid state controller, that sends a signal back and tells the battery, hey, turn on, I want it to do things. It gives you that isolation between the circuits. Another reason you can use relays is for logic purposes, right? On this car, you probably don't want heating and air conditioning working at the same time. Now, I don't know how this car is mechanized, but different cars, what you'll do is have a relay in there with a normally open, normally closed contact so that both systems can't run at once. If the relay's one way, one system will go. If the relay's the other way, the other system will go. In industrial world, with equipment in manufacturing plants, they use relays all the time, and they have what they call relay ladder logic, where you use relays laid out in a specific pattern to control machine functions. And you could do it with an interlock switch, right? Say on the car, you don't want the rear hatch to open unless you're in park, and the ignition switch is on. And you can use relays to set that logic. Now, we've been talking for several minutes here now about relays and what they do. What is a relay and what does it look like? Look at this picture that I've got here. The little dotted box kind of represents the outer bounds of the, that's the case of the relay, right? And the wires coming in and out, you'll see these are the connections. And the majority of relays in life are what they call normally open. And you'll see them noted on a print or on a wiring diagram as NO usually, meaning normally open. All of the relays have a coil of wire, and generally speaking, the coil of wire has an iron core. The wire's wrapped around an iron core that increases the magnetism. And what you're doing is building an electromagnet. So when you feed current into this coil, it builds a magnetic field that goes up and pulls that contact, that normally open contact, down and closes it. The contact has steel in it, so when you turn the electromagnet on, you pull the contact down, and then there's a set of contact points that make a connection. So you start with a power feed here, and then there's some kind of control input. It could be a switch, it could be a sensor, say on your fan it's a temperature sensor, and when the temperature sensor hits a certain point, it takes battery voltage and feeds it to the relay, and then the relay energizes and magnetically pulls down that contact. And then you feed that power from a power feed somewhere from the battery through a fuse, from the ignition switch in some cases. Some of them are hot all the time, but so you'll have a defined feed. You go through that normally open contact, and then it goes to your load, whether it's a fan motor or a hatch release or whatever you would like. And then in the cars it goes to ground. If you were doing it in your house, you probably got a return wire. But speaking from an automotive standpoint, that's the basic circuit. Now, I said electromechanical because that's the coil of wire and a contact design. In some of the newer cars, there are some things called solid state relays where they actually have transistors and semiconductor devices built into a little housing, and they perform the same function as a mechanical relay without the mechanical part, without the coil of wire. But for today, let's just stay with coils of wire and understand what we have here. Now, there are a bunch of options in relays. There are a lot of things you can do. The first thing is, a moment ago I said normally open relays. Well, now this one is a normally closed relay. So the contact has a spring load, and it's closed, and it'll pass current to the load. And then you come over here and you turn this control input on and let current go through the coil, and it pulls that piece of metal away and opens the contact up. The next one you can go through is option number 2. And in option number 2, there are quite a few of these in the world actually. These are the ones you can start even more to do logic with, because you have 2 contacts. One is normally open and one is normally closed. So when you energize the relay, you close this top one and you open this bottom one. So the top one, when you turn the relay on, you'll send power to that load, to that motor, or whatever device it happens to be, and turn it on, and then the normally closed one is going to turn off. And when you come back down to the power feed, to the control input, if you open up the control input, either a sensor or a switch, and de-energize it, then the normally closed will go back closed and turn that device on, and the normally open will pop open and turn the other one off. That make sense? Hope so. Now, there's something most people don't know about, and I'll tell you that I didn't know it as an early engineer, early in my career. I got myself in trouble with this at one point where I was trying to test a fan clutch. It was a clutch-driven fan with a coil in it, and I didn't realize that they had a suppression device in it, and I connected it backwards, and it had a diode in it for electromagnetic suppression, and I blew the diode out, and I got a big arc, and I damaged my setup, blew a fuse. But it taught me a lesson, you know, that 40 years later I still remember very vividly, because it was a moment of excitement, I'll just put it that way. In automotive and other vehicle usages, and you may find this in industrial equipment as well, it depends on the design, and the engineers who designed the circuit and chose the relay did things for a particular purpose. And every coil of wire has a magnetic field around it when it's operating and when it's energized. And every coil of wire has something called inductance. And I don't want to get too far into the weeds on what inductance is, but basically when you apply power to a coil, it takes some time for the magnetic field to build because there's a resistance to the current called inductance. When you turn the power off, that magnetic field has to go to zero and collapse. And when it does, it creates a voltage spike in the system that comes back the opposite direction, back EMF. And if you think about it in your car, you have an ignition coil. And if you study how an ignition coil works, I'll go back to the breaker point days, right? You'd run a current through your ignition coil, and then the breaker points would pop open and stop the current abruptly. The magnetic field collapses, and that induced energy in the secondary of the ignition coil, and that's how you got 30,000 or 40,000 volts to go fire your plugs. In these little relays, the spike isn't as big, but it's significant. And I'll go back and say, again, early as a student when I was working in brakes, the people who, it wasn't my project, but the people I was working next to had an electric motor powered hydraulic brake booster. It was, you know, when you stepped on the brake, the motor would fire up and it would drive fluid. And they were having trouble with the system where the system was, the circuit boards were being damaged and they were having trouble. Well, they had a coil in there and a relay that wasn't properly suppressed. And make a long story short, is if you looked at it on a meter or on an oscilloscope, it just looked like you turned it off and there was a little bit of a blip in the voltage. But when you put it on something called a storage oscilloscope where you could capture the event and look at it and expand it, when they turned it off at 12 volts, they were getting a voltage spike that was a couple of hundred volts. It was like 150, 175 volts pulse when they turned the system off. And that 175 volts was going back into their circuit board and damaging components. So, with that said, all of these relays, most of these relays will have a suppression device because when you open the switch, you'll get an arc in the switch, and the arc is noise. It'll make if you have an AM radio, it'll make your AM radio pop. It'll put electrical interference into adjacent circuits. Eventually it'll damage the switch, and the switch, contacts may burn. There are a couple of ways of doing suppression, and the one I've got shown here is a resistor across the coil. Now you can also use a diode, that's this symbol here. And the difference is that a resistor is a constant bleed across the coil. It's a parallel path for current to go. And the diode is a one-way device. So the problem I had with the clutch that I set on the fan was and hooking it up backwards is the diode resists current in one direction and is a dead short in the opposite direction. Very close to a dead short. So if you're testing one of these, you want to know what's in it. You can put an ohm meter across it, no problem, but don't put 12 volts across it unless you know the polarity and you've got the same polarity on it. Now, the engineers will tell you, there are different reasons, and you can go look up technical papers on, and go to one of the people one of the companies that makes relays, like Texas Instruments or whatever, and they have charts that will tell you what kind of resistor to use, what kind of a diode to use. Each one that you choose changes the time that it takes for the circuit to react. That's its whole purpose. But if you choose it wrong, then the circuit will not respond the way you'd like. So that's a big deal, and most people don't know that it's there. And so watch out. So here's one that I picked out of some service information from 3rd Gen Camaro days. And this one says, here's the horn relay. And you can see over here there's a coil. Over here there's a normally open contact. So you come down here and there's the horn switch. So when you hit the horn button, you close the switch. There's a slip ring and a brush in the steering wheel so that when you turn the steering wheel, when you hit the button and the button's on the wheel, you got to get it through to the steering column. So anyway, so that energizes the circuit. It pulls from a fuse up here, and that's it's a 20 amp fuse for the horns, so you could pull a pretty good current. Now over here, the one that circled says diode, so that particular relay has a diode in it, and as long as you keep 12 volts across the correct polarity, this is the feed, and this goes to ground, you'll be good. If you reverse that polarity, you'd blow that diode out. Now the relay might still work, but it wouldn't work correctly, and you'd probably have electric static, and systems wouldn't be good. Just a caution. So again, if you want to test these, this is a simple, it's normally closed. You can use an ohm meter and you can try to test the coil, but if they have a resistor across the coil, you can't tell if the coil's burned out, because if you don't know how big the resistor is, you'll see a resistance. It'll conduct current even if the coil's bad. So you can check and make sure there's power coming in. You can make sure the grounds are good. You can come up on the high side and verify that you have a normally open or a normally closed circuit and the contacts are correct, and you can measure the power out to the load. So if you want to know if that relay is good, you have to energize it, turn it on, and make sure that it's either normally open or closed, and test the power going through to the outside. That could be kind of hard, and I'll say the reason I've got this relay in my hand that I keep telling you is out of my Suburban. This is for the rear hatch on the tailgate, and I was having trouble with the rear hatch. The hatch wouldn't open consistently. You'd push the button, and sometimes things didn't come loose. You wouldn't hear it click, and the glass wouldn't open. And I tried testing things, but it's very difficult, because in that case you push a button and the relay gets a pulse, ka-chook, up and down, and it's gone. And it's very hard to get a meter on there and then run up to the front of the car and push the button and get a pulse and read the pulse on the meter, which the pulse is only a fraction of a second long. So I figured out what this was, went down to Napa with it, and they sold me a new relay that was equivalent, and I plugged it in and it's been working fine. I don't know what's wrong with this one yet. Everything electrically from the outside looks good, but it was only working about half the time, so something in there wasn't right. And once again, when you're testing, observe the polarity, make sure it stays the same. Connections, how do you connect to relays, right? our old cars, like these from the 80s, typically speaking, they just have letters, right? This is from the 1990 book. Here's the fuel pump relay, and you'll see that it's got terminals A, C, F, and D. Gee, they don't even have a B terminal on that one. But the terminals just have letter designations, and you need to go back to the service information to find out how it's wired. And incidentally, here's one with a normally closed contact and a normally open contact. And when you pull the coil, there's a test terminal here for the fuel pump. And when you pull the fuel pump in normally, it turns that test terminal off. And here again, you can see from the ECM is feeding battery power out to the fuel pump relay. And the coil is being driven by this one that's called fuel pump relay drive. So it comes through here, it's feeding power. It comes around here and goes back to a ground and goes to an engine ground there. Now, on newer vehicles, and you may even find these on some of our 80s vehicles, I haven't pulled the relay out, like the horn relay, out of the fuse block area. For many years, there's been a DIN spec. There's a German standards organization called DIN. So they have a method of numbering connections. If you go into European cars, you'll often find these numbers in many places in the car. In the US, we don't always do that, but we've adopted it at least on relays. So the standards are that your coil input has a number 86, and that's molded into the relay. It's molded into the case. The ground side has an 85 molded into it. The relay contact for a normally open is 87, and for a normally closed is 87A. And the feed from the power coming in is 30. Now, there are other variations of this. I mean, there are a lot of relays out there, and these relays are available with 2 normally opens, 2 normally closed. The industry has a lot of different options. So if you have a relay like this that fails, you need to look at your service information, or you need to really look at the relay to understand what it is. I mean, this is a 4-pin DIN styled relay. And here's an up close of it. Okay, so this is my Suburban relay. So on the bottom, here's an 87, that's because it's a normally open. Here's an 87A, which would be for a normally closed if it was there. And you'll notice that pin's missing. If you had a 5-pin relay with a normally closed contact, you'd have that. Then there's 85 for the ground, there's 86 for the power coming in, and there's 30 for the high load power coming in. And if you flip this relay upside down, on the other side, they've actually got, this is the schematic, so there's 86, that's the coil power coming in, there's the 85, that's going out. This little device on the bottom is I think a resistor, based on it doesn't tell you what it is, but it looks like it's probably a resistor to take energy out of the coil when you open it. And then this is your switch circuit. It's normally open, and power in, power out to the load. And I will tell you is also that when you get to the bottom, these terminals, the terminals have different patterns, different manufacturers, different sockets. So, they aren't always a pattern of 4. There are different ways that you can lay these out. So, I hope that helps. And if you have other questions, send them back. But that's what we do with relays. That's how relays operate, and that's why they're important to you. And without relays these days, your cars won't run. Once again, hope that helps, and that's all for now.